computer. Okay. But yeah, if there's any questions, just let me know. Hopefully this course isn't too bad. We have a month left to just kind of put that in the back of your head, make sure you're staying up on Amatrol. I know a couple people have mentioned that the alternators Amatrol is broke or isn't letting them like complete it or something like that. So if that's the case, let me know, because I might be able to like give you a reattempt on it, and that might fix that issue. Or if you complete it and it doesn't give you a grade, also let me know, because I can log into like Amatrol, like the actual website, and I can type in your name and it'll give me a grade, and then I can enter it into JetNet. So if it's ever not like showing on JetNet, let me know and I can adjust it. The other quick thing to just like basic administrative things. So for your Amatrol, a reminder that anytime you get a 70 or above on the quiz portion of the Amatrol, that's the only portion that's kind of to your grade, it will be 100%. So I think when JetNet translates it like into your grades, it will like reflect it as like an 82, a 75, whatever you get. But just know that I go through it every week and like or every 2 weeks and adjust them so they're 100%. So, and if they're below 70, adjust them so they're zeros. But that doesn't happen often, but just so you know. But okay, so we'll get started. So this week, the main idea is inductive reactance and inductive circuits. So that's kind of the new term that's thrown at us. So last week, we talked a lot about capacitance and capacitance reactance. You'll see that this week really mirrors that, except now instead of capacitance, we're talking about inductives or inductive circuits. So the reason I said inductives is because I think of capacitors and inductors. So those two kind of sides of it come into play as well. So, okay, so to kind of start off here, so what exactly is inductance? And I think when talking about inductance, it's important to talk about capacitance as well, just because I think they it's easy to get the two terms confused, and I think, you know, talking about them both at the same time helps show the differences better. So as we remember from last week, capacitance is essentially just the ability to store energy in the form of an electric field. So this idea of an electric field we didn't really talk about, but it was because nothing else really came into play. So the only thing that really mattered was that it was just the ability to store energy. You know, and we talked about that and how capacitors store energy, you know, with the two metal plates, and I showed that kind of video. So hopefully you remember that. But inductance is essentially the same concept, that it has the ability to store energy, but now it's in the form of a magnetic field, so not an electric field. So that's a key difference between inductance and capacitance. So capacitance stores energy in the form of an electric field. Inductance stores energy in the form of a magnetic field. The other things that are really important to note for inductance, so it is measured in something called henries. So you're going to get that new, a lot of new equations and do calculations with henries. So that's denoted as just an H, or sometimes if it's, I think, microhenries, it'll say MH, M little h. So just make sure you're not confusing that with hertz, which is, you know, the unit for frequency, just because there are some mathematical calculations where you're going to have to use frequency and use inductance. So don't confuse the H's, I guess, there. So I think hertz is denoted HC. So the other thing to note here too, so in like equations, when they write like X equals whatever, inductance is denoted by the letter L. And I'll point that out when we do a math problem. So I think kind of going off of all this, you know, now we know that one's electric fields, one's magnetic fields. So I think it's important to talk about what the heck that means. So basically, I think this chart here, which I have, there's a really good resource down here if you're still confused, but I think this is like a great side-by-side comparison of all the different components of the fields and kind of how they're different. So this kind of just shows at the beginning here, this is probably the main difference, and especially the main difference as it relates to this course. So electric fields are produced by voltage and magnetic fields are produced by current. And in the next slide, I think that's going to kind of tie back to inductance and capacitance. So just keep that in mind. Just kind of memorize it, write it down for now. The other important thing to note here, I think that second one is a really good one too. So it's the fact that there's a direct relationship between the voltage and the resultant field, so the electric field. So the higher your voltage, the higher that electric field, or the stronger, I guess it's going to be. Likewise, for a magnetic field, the greater the current, so the faster it's moving, the stronger your magnetic field. It gives the important things here. So it shows the different units. That's important. So I don't know if you've ever heard of the units of Tesla or Gauss, I think it's called, but just if you see those units. And later on in your courses, just note that, it's referring to magnetic fields and currents and all of that. Lastly, I have this diagram because I don't know if you remember, I pulled this up, I think the first week of course, but just showing like a visual of electric fields and magnetic fields. So electric fields, they operate by having the positive side and the negative side, and magnetic fields operate by having a north pole and a south pole. And if you remember, I talked about this because I said the way that they work is those two forces like repulse each other, and we talked about the relationship between repulsions and attractions, and it's the same kind of principle for North Pole and South Pole and positive and negative. So yeah, so hopefully that's clear. So to kind of tie all this back into inductive and capacitance. So we talked about capacitor reactance last week as well. So there was an equation that I'll jog your memory on the bottom here. But we talked about capacitor reactance as it's the opposition to the change of voltage across an element. So, and that makes sense if we go back to this, because we know that capacitance here is stored in the form of an electric field, and we know that an electric field is produced by voltage. So it makes sense that capacitor reactance is the opposition to the change of voltage across an element. Likewise, for inductive reactance, so that is essentially the name given to the opposition to a changing current flow. So inductive reactance is really the same thing as capacitor reactance, except instead of voltage, it's flow or current flow, which makes sense if we go back to this, because we know that inductance is the ability to store energy in the form of a magnetic field, and we know the magnetic field is produced by a current. So it makes sense that it is reactance of inductive reactance is a name given to the opposition to a changing current flow. That was a mouthful, but hopefully all of that kind of ties all in together and helps you memorize it. So as you'll see in a minute here, our equations that we use to calculate inductive reactance, or times that we have to use inductive reactance, oftentimes the equations are very, very similar, if not the same, to the capacitor reactance. It's the same principle, and it's ultimately because of the fact that these two terms are very much related. So the other thing to just note here, so inductive reactance, like resistance and like capacitor reactance, it's measured in ohms. So that is a very important thing to note too, just because when you're doing all these equations, and a lot of times the units can be confusing. So I recommend, I don't know if I said this last week, but I recommend maybe writing in like on your computer, or writing a notes, however you take notes, all of the different terms, the key terms that we've talked about the last couple of weeks, writing what the symbol looks like in an equation, and then writing what the units are for that equation. So for example, writing inductive reactance, this little symbol here acts with a little L is how we denote inductive reactance. And then the unit obviously is ohms. So I think that will help, not only help your understanding of this course, but also help when you're doing all the math problems. Okay, so now to the fun stuff. So this is a little bit different. Actually, we didn't really have any problems that use rates, I guess, as in the previous week. So I'll maybe take this one a little bit slower. But essentially, this on the right here is a new equation that comes up for this week. And this is called Ohm's law for an inductor. So when talking about an inductor, there's an Ohm's law, just like, our typical Ohm's law we have, which is V equals I times R. So this is an equation is definitely one that you'll want to memorize and fully understand. So to kind of break this down component by component, what this equation is saying is that V, which is our voltage across the inductor, and instantaneous voltage is just referring to voltage at a given point in time. So it's saying at this instant, what is the voltage? So in this instant in the circuit, what is the voltage? So V equals L, which is inductance in henries. So we talked about that, right? The inductance is measured in henries and denoted in the letter L. So that's what the L stands for. And then this new term, di over dt, is where we get something that can be kind of challenging, but hopefully if I break it down, hopefully you'll understand it. So di dt, it might look familiar if you've taken any calculus courses. When doing things like integrals, which, like calculus is all about derivatives and integrals, you oftentimes see like this weird symbol where it's like exactly like this, like dx dt, dy dt, where basically it's like two sets of letters divided by two sets of letters. And almost all the time what that is expressing is that it is a rate. So this di dt here, all it's saying is that it's L times a rate. And this rate here is the instantaneous rate of current change. So amps per second. So that's basically why there's a I there and a T there. So it's saying, what is the instantaneous rate of current change? So what is I, or what is your current, divided by time? And amps, we talked about amperes, or amps being the measure of current. So ultimately, all this equation is really saying is that voltage, so your instantaneous voltage or your voltage at a given place in time, can be found by multiplying your inductance by your current divided by a given set in time. So to kind of show an example here, so I think that's probably the easiest way to break it down. So let's say that we have an inductor with an inductance of 6 henries. Okay, so right away we know L is 6, right? Because L is the inductance in henries, it tells us that. Then it tells us the current changes from 40 to 50 amps in 1 second. So this is a perfect example of a rate. So as you can see, they're giving us that in 1 second, it's the current is going from 40 to 50. So in order to calculate a rate, it's just a distance over a time. So that's, again, what this is. So the distance over a time, but I like to think of it as I is current divided by time, which is T here. So distance, so 40 to 50, so that is 10 amps, right? So 10 divided by 1 second gives us just 10. So that's kind of why this here says this. So di over dt, which is the rate, equals 10 amps in 1 second. And obviously 10 divided by 1 is just 10. I'll probably do another example in a minute here that gives it the rate in like 5 seconds, because you can also do the same problem. It might not be 1 second, it might give you a rate in 10 seconds, and you can still solve it by the same principle by just knowing you're doing the change of the current. So however, the difference of the current divided by the time. So I know I'm talking a lot about this one problem, but I just want to make sure this concept is clear, this di dt. So just, note that it's this. So we can just do 6 times 10. So 6, which is L, 10, which is di over dt, to get 60 volts. So this is mirrors an exact problem that you could see on the quiz. So hopefully this makes sense. To kind of just show, so let's say that we had a problem that instead of 1, it said 5. How would we do this? Oh. So this problem can be solved the same exact way. The only difference here is that our rate changes, right? Because in 5 seconds, we're going 40 to 50, or in 5 seconds, we're going, we're increasing our speed by 10 amps. So the way that you would calculate di dt here is the same way. So di, so the change in the current, so it's still going 40 to 50, right, which is 10, divided by, so dt, so it's instead of going in 1 second, it's going in 5 seconds. So this would equal to di dt, if that helps. So all I was showing here is that you can still calculate rates when your time is longer than 1 second. So I just wanted to make sure that was clear. So again, it's just taking the difference of the amps and dividing it by the total time it takes to make that difference. So hopefully that makes sense. But if it doesn't, just send me an email, or I can do a couple more examples later on as well. Okay, so this isn't a question from the quiz. And I put it in here because I think it is a very interesting question, and a lot of people have gotten it wrong. And this is why. So this problem says, true or false, a DC current with 2 amps and a 2 Henry inductor will have an induced voltage of 4 volts. Okay, if we looked at this, most people, and the reason a lot of people got it wrong is because, and if you haven't done it yet, that's great, you can get it right. Or if you have any more attempts left, you can also get it right. So just note this one here. So the reason a lot of people got it wrong is because they just quickly saw, okay, so we have amps and we have our inductor, and they knew that it was L times this. So they did 2 times 2 and thought, okay, yeah, that equals 4 volts. But what this question is missing is that it's not telling us a time, right? So going back to this equation, we know this di over dt, it's a rate. So it's not just amps, it's amps in a given amount of time. So the reason this problem is false, the reason that it isn't that, is because this problem is actually insolvable, because we don't know what the induced voltage is or will be without knowing how quickly, or without knowing, through what time period, or how long does it take to get to 2 amps. So, I just thought that one was interesting, and I wanted to talk about it a little bit more, but hopefully that makes sense. And now you can see kind of why I focus so much on understanding this component. Okay, so the next equation that kind of comes up in this week is very similar to something that you might have done in previous courses, especially if you've dealt with frequencies before, because that 6.28 number might be familiar to you. And if you used your calculator right now and did 2 times pi, you will see that 2 pi is actually just 6.28. So this equation you might have seen before, but instead of being 6.28 there, it's just 2 pi. And that all relates back to the sine, the cosine, and all of that. But okay, so now frequency comes back into play. So we talked a little bit about that frequency last week as well. And this is kind of why I mentioned making sure you don't mess up the HZ and the Henrys, because they are totally different units. So you can calculate inductive reactance with this equation here written on the right. So Eddie talks about these in the videos. So I kind of just screenshotted this equation because it is important to note here. So what this equation is saying is the inductive reactance, which is X, which really this should be X with a subscript L, equals 6.28 times F, which is frequency, times L, which is your inductor value in Henrys. So an example of using this equation is shown here. So let's say that we have a circuit with 10 mH inductor and a frequency of 3000 hertz. What will be the inductive reactance on that inductor? Okay, so to kind of write down what we know. So we know that F equals 3000 hertz. And we know that L, which is our inductor, equals 10 mH. So this is where it can be a little bit challenging. So, and where units come into play, and where I've seen a lot of people get this question wrong, is this mH. I don't know if you have any prior background in like unit conversions, but basically all this is one H or 1 Henry equals 1000 mHs. So since we are given 10 mHs and we know that 1000 mHs equals 1, we should ultimately divide this 10 by 1000. And that will convert it to Henrys. I don't know if Henrys or I don't know if it's IE. I'm an engineer. Sorry, I'm not good at spelling. Okay, so now we can just easily solve this equation, right? So it's just 6.28 times F, which we know is 3000, times 0.01. and your answer should be 188.4. So this problem is really easy. It's just as simple as multiplying three things, but just, recognize this here, that if it is mH, you'll have to convert it to Henrys. And I'm actually curious, I'm going to look up real fast what mH stands. I'm assuming it's megahertz or mega Henrys. See, I just messed up frequency and mega Henrys. Aha, yes. Maybe. That makes sense. Okay. So it is 1 millihenry, it's called. So, and that makes sense because a milli is obviously smaller than a Henry, right? So it's like saying like a milligram and gram. It's kind of the same comparison. So there's 1,000 milligrams in 1 gram. Likewise, there's 1,000 millihenries in 1 Henry. So sorry, I just wanted to look that up, make sure I was saying it right. So yeah, just make sure you're using that conversion if you have a problem like this. So again, to just convert millihenries to Henrys, just divide by 1,000. Okay, so the next thing to talk more about these sine and cosine and shift phases. So this is just another important one to note. I know like we talked a lot about like the AC and the DC phases and like how they're denoted on a graph over time. So I just wanted to pull this up here and show you the voltage and the current graphed over time, just because the main idea here, and it's kind of going to come up when we talk about these math problems in a minute here, is that voltage is leading by 90 degrees phase shift. And you can see it perfectly, or I guess visually in this graph by what they're writing here. So I think it's nice to look at this. So that 90 degrees is from the base here to the peak here. And obviously you can see that the base here is in front of that one. So that's kind of why it's leading by 90 degrees. So, okay. So the other thing that is kind of tying back into AC and DC is this idea that a capacitor blocks a DC, but not an AC current or an AC circuit, I'm sorry. But on the flip side, an inductor blocks an alternating current circuit, but does not block a DC. And I think that's kind of a challenging concept. So I think it helps to see it in a visual. So this top one here, we can see a kind of a visual representation of a capacitor, right? So we talked about those two metal plates, and it's showing kind of visually why a capacitor blocks DC, but not AC. And that's because AC is, since it is that sine wave that we talked about at the first week of course, it kind of goes over and under that capacitor, whereas the direct current is just a straight line and it's going right through and it's just going to hit that plate. And it also makes sense when talking about this because we know that a capacitor is, if we go back up here, related to an electric field, right? And this is a perfect example, where am I, of an electric field. So on the opposite end, so when we're talking about inductance, we are talking about a magnetic field, which we talked about at the beginning, right? And a current for a direct current is going to go straight through a magnetic field. So in some of these videos, I'm not going to touch on it too much because in an effort of time, but we talked about like in the videos and in some of the questions on the quiz, they'll talk about like the coiling of the wire and how that's related to a magnetic field. These are just examples of it. And you can see that for a direct current, since it is a straight line, it's just going to go right through that magnetic field. Whereas you can picture it, an alternating current or an AC circuit is just going to go up and down and up and down. So it's not going to ever go through it, right? So hopefully that kind of helps that concept, because I do think it is a couple pieces of like conceptual knowledge, I guess, that's important for the quiz. So just knowing that a capacitor blocks DC but not AC, and an inductor blocks AC but not DC. So this is an example of an inductor blocking, well, it doesn't show a blocking AC, but it shows it passing DC. Okay, so for the last little bit here, I first want to talk about, I'm going to go up one in a minute here, but we talked about this a lot last week. So hopefully this idea was clear to you. So, and hopefully this looks familiar, but this was just how we did some math calculations using impedance. And, you know, we use these equations ultimately to find our current. So I'm just going to leave this up for a minute in case you want to refresh your memory. But if you want me to talk about it, I can gladly talk about it. But I also don't want to repeat it all if you don't want me to, since we did talk about it last week. So the reason that I kind of wanted to refresh your memory here on, you know, drawing this triangle and then obviously, you know, doing this component here, so the square root of xc squared plus r2 squared, is because this whole idea comes back again for inductive reactance. So how I talked about at the beginning, how inductive reactance and capacitive reactance are very, very similar. This is exactly it. So a quick recap here. So in one of the videos for, I think this is the second video for this week, this diagram is drawn here. And this is a pretty simple example that I want to kind of walk through. So what they're drawing here is, this is a generator, this is a circuit, obviously, and then we have, you know, these Z lines, I guess, is to denote resistance, which hopefully you all remember that from ELT 106, 120, drawing resistance with that zigzag line. So 100 ohms, this little quill line here, that is representing inductive reactance. So that I just wanted to note so you know that in circuits, it can be challenging when they're drawing like all these different symbols and everything. So just note that this is resistance and this is inductive reactance. So when talking about impedance last week, I mentioned that it is the combination of reactance and resistance, right? I showed this triangle and said, you know, impedance here is the connecting piece between reactance and resistance. So it takes both of those into play. And that's why, you know, when talking about Pythagorean's theorem, that's why in order to calculate impedance, we have to do that, this equation here, which is very similar to a squared equal, or c squared equals the square root of a squared plus b squared, or c equals the square root of, yeah. But anyways, so likewise, we can solve equations very similar to last week by using that same principle. So firstly, he drew the diagram here. Then secondly, he drew a triangle. So you can see that it's kind of difficult. I'll zoom in a little bit. You can see that for this equation, he is calculating Z, which if we go back to what we talked about last week, Z is just our impedance. So like calculating impedance using capacitive reactance and resistance, this week we're calculating impedance using inductive reactance and resistance. So we know here that we have 100 ohms and 100 ohms, right? Because 100 ohms here. And then you can easily use this equation, Z equals R, the square root of R squared plus X squared, and solve for Z, which is impedance. So if you did the math here, you would type into your calculator the square root of 100 plus the square root of 100. But that will not give you the right answer because you have to do 100 squared plus 100 squared. And that'll give you 141. So all that's telling you is that when you're, and that's kind of, or he didn't write it here, but just all that's telling you is that your impedance is 141. So I'm going to write that here. And again, I did that by doing the square root of 100 squared plus 100 squared. So I think I wanted to write this out too, just because in like textbooks, sometimes they will kind of represent it written like this. So just for like your knowledge and former course and courses you might take. So this is just showing like how you would type it into a calculator. So you type in the square root function on your calculator, parenthesis, and then 100, and then that caret sign, which is that little like upside down V squared plus 100 squared. So again, that's what we use here, which is just the square root of the impedance plus the reactance, both squared, will give you impedance. So the last step here that he did in the videos is like calculating current last week, you can calculate current the same way using Ohm's law, because now since we know impedance, we can do I equals V divided by Z, which is just our voltage divided by Z, which we calculated as our impedance. So I don't think it cut off right here. You can see it right here, but it does give you that the voltage for this problem was 120. So that is why here this I divide equals V divided by Z is just saying that you can calculate current by doing voltage, which was 120 given in the problem, divided by impedance, which was 141, which we found by doing and using this equation by drawing the triangles. So yeah, so basically that is the main idea from this week. It's just using the same equation, the same principle, but instead of talking about capacitive reactance, we're talking about inductive reactance. The other thing to note really quick here is that the triangles are reversed for capacitive and for inductive reactance. So you can see here that on this one, this triangle here looks a little bit different than the one drawn here, right? The longer edge is going this way. That is just because it is reactance, inductive reactance. So I would maybe draw like a diagram there showing that inductive reactance looks like something like this, where you have your long leg of your triangle or your hypotenuse or your impedance, all the same words there. Looks like this. And then when you are using capacitive reactance to calculate impedance, when you're drawing that triangle, it looks like this. So the long edge is this way. Just because it's sometimes going forward in the remaining weeks, that concept of like the changing triangles and the difference in how they're looking is going to come into play. But okay, so I think I reached, those are just some additional resources. I think I've reached the end of my slides today. So I'm gonna stop sharing, and then I'm gonna stop recording as well. So if